All right, KS23003 students, welcome to your first real deep dive into signals and systems. Before we can analyze or do anything interesting with a signal, we all need to be on the same page about how to describe it. We need a common vocabulary. So this explainer is going to give you exactly that, breaking down the fundamentals of signal classification right from your week 1 materials.
So here's our game plan. We'll start with the why. Why do we even need a common language for signals? Then we'll jump into the 4 core ways we classify them, looking at time, amplitude, patterns, and predictability. After that, we'll put it all into practice with a little challenge, and we'll wrap up by clearing up a super common mistake that trips a lot of students up. Okay, let's dive right in with the most important question of all. Why bother classifying signals? Why is this one of the very first things you're learning as an engineer in this field? Just think about it for a second. The world is just buzzing with signals. You've got voltage in a circuit, radio waves, the audio coming out of your headphones. It's everywhere. Now, imagine if every engineer had their own unique way of describing these signals. It would be total chaos, right? How could anyone collaborate? It's a huge communication problem that we absolutely have to solve. And the solution, well, it's a standardized classification system. This framework is that common language we've been talking about. It means that when you describe a signal, any engineer anywhere in the world knows exactly what you're talking about. Honestly, if you master this, you've mastered the bedrock of this entire course. So, let's get into the nitty-gritty. Our first 2 dimensions of classification focus on the absolute fundamentals of any signal graph: the horizontal axis, which is usually time, and the vertical axis, which is the amplitude.
First up, we've got the time domain. Is the signal continuous time, or CT for short? That means it's defined for every single possible moment in time, what we write as x of t. Or is it discrete time, or dt? That's where the signal is only defined at specific, separate points in time, written as x of n. And right away, the notation itself, the parentheses versus the square brackets, that's your first major clue.
Next, let's look at that vertical axis, the amplitude. An analog signal can take on literally any value within a certain range. Just picture a smooth flowing sound wave. A digital signal, on the other hand, is different. It can only ever be one of a few specific, predefined levels. The technical term for this is that it's quantized. Okay, so we've covered the axes. Now let's talk about the behavior of the signal itself. This is where we get into patterns and predictability. This one is all about repetition. Does the signal have a pattern that repeats itself exactly forever and ever? If it does, we call it periodic. And for it to be truly periodic, it has to satisfy a very specific mathematical rule. The signal's value at any time t has to be exactly the same as its value 1 period later. If it never repeats perfectly, well, then it's aperiodic. Simple as that. Let's make this real with a classic example you'll see all the time: cosine of 4t. So how do we find its period? First, we just identify the angular frequency, that's omega naught, which in this case is just 4. Then we plug it into the formula for the fundamental period. T naught is 2 pi divided by omega naught. Pop in the number and you get 2 pi over 4, which simplifies right down to pi over 2 seconds. And there you have it, that's the period. And for our last dimension, we ask, can we predict it? If the signal can be described by a perfect, precise mathematical formula, like that cosine wave we just saw, then it's deterministic. You can know its exact value at any point in time. But if you can't predict it exactly and you have to start using things like statistics and probability to describe its behavior, then you're dealing with a random signal.
Now this is a really important point. These 4 classification pairs are all independent to each other. Every single signal gets one label from each pair. So, for example, you can absolutely have a signal that is continuous time, analog, aperiodic, and deterministic, all at the same time. These categories don't cancel each other out.
All right, that's enough theory for now. Let's actually put this framework to the test, shall we? We're going to classify 3 very common signals that you'll see throughout this course using every dimension we've just learned. Let's just walk through this table one by one. First, we have that decaying exponential, e to the minus t, u of t. Okay. It's defined for all time, so it's continuous time. Its amplitude is continuous, so it's analog. It keeps decaying, but it never repeats, so that makes it aperiodic. And since we have a perfect formula for it, it's deterministic. See? Easy. Next, cosine of 6t. Again, defined for all time, so continuous time. Continuous amplitude, so analog. This one definitely repeats, so it's periodic. And, just like the first one, it's defined by a clear mathematical rule, so it's deterministic. And finally, let's look at -1 to the power of n. Those square brackets are a dead giveaway. It's a discrete time signal. Its value can only ever be +1 or -1, so it's digital. It flip-flops and repeats every 2 samples, so yep, it's periodic. And because we have the exact formula, it is of course deterministic. It's a really systematic process once you get the hang of it.
Okay, before we wrap up, I want to tackle the single biggest point of confusion for new students. It's a really easy mistake to make, but once you see the difference, it'll stick with you for good.
I want you to burn this idea into your brain. Aperiodic does not mean random. They are not the same thing. Let's think back to that decaying exponential signal. Does it ever repeat? No, so it's aperiodic. But can we predict its value at any time? Absolutely, we have the exact formula. That makes it completely deterministic. See, aperiodicity is about repetition and randomness is about predictability. They're two totally different ideas. So, there you have it. Mastering this classification framework is your essential first step. It gives you the language you'll need to talk about any signal you encounter. And this prepares you directly for what's coming next, which is actually performing operations on these signals, things like shifting and scaling them. So the question I'll leave you with is, now that you can classify them, what can you actually do with them? Thanks for watching.